Let's look at entropy or disorder. It is given the letter symbol of S, and remember this stands for disorder. Anytime you see the word entropy, think disorder. Entropy describes how energy is spread out within a system. All systems tend to move towards maximum entropy or maximum disorder. Entropy is a measure of the molecular randomness or the disorder of those molecules in a sample. When we look at entropy, we are calculating the number of arrangements for a system is another way to look at it. So let's look at this randomness. Let's say I have a gas chamber and I have exactly one atom. Well, there are two possible relationships. I can have it in the right-hand chamber or in the left-hand chamber. So there's a 50% chance of finding one of the chambers empty. If I have two gas atoms, then I have more arrangements. They can both be in the right, they can both be in the left, and I can have one of each of them in the left and the right. So as far as the probability goes, it's more likely that I'm going to find an even distribution. So 50% of chance I'm going to have one in each of the chambers. When I add 4 atoms, now my different probabilities increase. But we tend to find that the gases will completely fill their chamber and they'll fill it evenly. And the reason why they'll do that is because there's more of a probability of them being evenly dispersed. So this is the disorder that we're looking at. So you would not think that all of the gas molecules would be in one chamber. You would think the more logical arrangement would be that they're evenly distributed. And there's more probabilities of that distribution. Entropy, as I said, is S. It's a measure of the disorder of the system. And just like our enthalpy, where we can take the sum of the products minus the sum of the reactants, we can do the same thing with being given entropies. Let's look at what the positive and negative sign means for entropy. Remember, entropy is disorder, so if I have a positive value, this is an increase in disorder. If I have a negative value, then that is a decrease in disorder. And I know it's a double negative, but just remember, anytime you see a delta S, that means disorder. The total energy of the universe is constant, so that is not changing, but the entropy is increasing. We tend to have positive values for disorder. And you should know that during a phase change, when we're going from a solid to a liquid or from a liquid to a gas, then our entropy would be 0. The second law of thermodynamics says that thermodynamically favorable processes always proceed in such a way that the entropy of the universe increases. So that's why we get a positive value of our delta S. So here's just a funny cartoon with a boy in a messy room saying, I blame entropy. But this is how processes tend to go. They tend to go from order to disorder. If we were to graph the entropy, we would see that our solid has the lowest entropy, and that is because it is more orderly. When I go from a solid to a liquid, we see that the entropy does not change when it's going through that phase change. This is when the entropy is 0. But then as soon as we have a liquid, we see that there's an increase in entropy, especially as heat is applied. Again, when we go through another phase change, we have our entropy is 0. When it's finally a gas, then we see that the gas has a lot of entropy. And this is because our gaseous particles have more freedom to move than the liquid particles, and so therefore our gaseous particles will have more disorder or more entropy. So this is a positional entropy that we've been talking about. Solid has less disorder than liquid, which has less than gas. Anytime you have a gas compared to a solid or liquid, it would have much more entropy. And that's because the disorder, the arrangement of them, the different possibilities of arrangement are much more in a gas than in a solid where it's locked in place. Entropy also increases when a solid is dissolved. So if you look at the solute that is dissolving, there are more possible arrangements of dissolved pieces versus when it was just a solid. However, if you are looking at a water molecule and looking at its entropy, we see that our water molecule actually has less entropy or less disorder, and that's because it's locked around that ion. It forms that ion dipole. And so that is a more orderly arrangement. And so if you're looking at the point of view of the water, there's actually less entropy. You can also look at a balanced chemical equation with entropy to see if the disorder is increasing or decreasing. And in this example here, we have an increase in disorder or a positive delta S. And I know that is the case because in this gaseous reaction, my ammonia, I only have 2 moles of it, but I see that I have 1 mole of the nitrogen gas and 3 moles of the hydrogen gas. So there are fewer bonds, therefore fewer restrictions on motion of the atoms. So there's more arrangements with 4 moles versus 2 moles. And a lot of your problems with entropy are going to be like this, looking at a balanced chemical equation and just trying to figure out what's going on. So it is good to look at the states of matter. In this one, I should have put all the little g's for gases, but I can see that I'm gaining more gas molecules, so therefore my disorder is increasing, and I would say it has a positive delta S. Briefly, the third law of thermodynamics says that the entropy of a perfect crystal at absolute zero is 0. So that would mean my solid is a perfect solid, so there's no disorder at all. But when we look at molecular motion, even of a solid, we see that there's different arrangements. So they're vibrating in place. So at any one point, I could take a snapshot, so to speak, of the solid, and I could see that some of the solid molecules are going to be moving away from each other. Some are going to be a little bit close. So there is disorder in a solid. Entropy also increases with an increasing molar mass, and it's not the mass that's causing this disorder, it's that there are more subatomic particles. And so molar mass is just a way to describe the size of the atom. If you have a larger atom, that means you're going to have more protons, more neutrons, more electrons. Therefore, you will have more disorder because the more electrons you have, then the more possible places they can be in that electron cloud around your molecule. And so we can look at our entropy trends down here. So looking at this first example, I have hydrogen versus oxygen. Oxygen is a larger molecule, and you can see it has more disorder, and that is because there's more electrons, therefore there's more possible arrangements. The second one shows our halogens, so as I go down the periodic table with my halogens, again, because iodine has more electrons, more protons, there are more different arrangements that you can have versus the fluorine, which only has 9 protons each and 9 electrons each. And then here's just some common molecules that you can see that the larger the molecule, then the more disorder that you have. And you see that trend through the next two also. So the larger the molecule, therefore, the more different arrangements you can have of where those electrons can be on each of their electron clouds. So therefore, you would have an increase in entropy. Now, you wouldn't say, for an example, that it has a higher molar mass. You would talk about more disorder because there's more different arrangements with those larger molecules because they have more electrons and more protons. So in summary, there's going to be a lot of qualitative questions with entropy, so you just kind of have to analyze and look to see where there's more disorder. So you can look at the states of matter. So gases will have the most disorder. You can look at the volume that a gas is occupied. So if the pressure decreases, the volume would increase. So therefore, the gas would expand. So there's going to be more places where you can find that gas in your container. Having the molecule vibrate faster, with a temperature increase, that would increase the disorder. Also having the more molecules, so that's comparing the reactants to the products. If you have more moles on the product side, therefore you're going to have more different arrangements, more disorder. And I already said the states of matter. So solid to liquid, liquid to gas, that would increase the entropy. And anytime you're dissolving something, that solute would have to form a solution, that would have more entropy. So let's just go through and practice what's happening with the entropy with each one of these. And so we're going to put a plus sign for an increase in disorder and a minus sign for a decrease in disorder. So go ahead and stop the video and see if you can figure out each one of these, and then we'll go over the answers. So the first one, A, the evaporation of alcohol, I'm going from a liquid to a gas, so that is an increase in disorder. The freezing of water, I'm going from a liquid to a solid, so I'm making it more orderly or decreasing disorder, so I should have a negative delta S. Compressing an ideal gas at a constant temperature, so that means I'm increasing the pressure or decreasing the volume. So I am making the container smaller. So this means there's there's smaller number of places where those gas molecules can be, so that is decreasing the disorder. Heating a gas at a constant pressure, so as I increase the temperature, the molecules are going to move faster, so that means there are more probabilities of where you would find them, so that would be an increase. Another state of matter, solid to a liquid, that's an increase in disorder. On this one, it looks like I have two gas molecules going to a solid, and so that would be a decrease in disorder. And the next one, I have one gas molecule going to two gas molecules. That would be an increase in disorder, so more probability with having two versus one. And then I have a gas going to a liquid. That's a decrease in disorder. On this next one, it looks like I have a solid solute and then it's put in water, so it's dissolved. So this would be, for the solute, an increase in disorder. And then on this next one, both a mole of oxygen, but I'm increasing the temperature. And we actually have a little chart here. So this one right here would be the higher temperature. The blue would be the lower temperature. So you would have a higher entropy in the one that has the higher temperature. And you can see that you just have a wider range of molecules going different speeds. So again, you're going to have slow ones here and faster ones over here. So there's going to be more probability in that temperature increasing. Whenever we work with entropy, you need to be very careful with your units. If we're doing a quantitative analysis problem, that is because entropy is really, really tiny, and so they represent it as joules. Everything else is measured as kilojoules. So delta H is measured as kilojoules, and later on when we talk about delta G, it's also kilojoules. Also, the enthalpies of formation can be zero, so that's the delta H's can be zero, but not if you have a delta S. So it will not be zero except if you're at a phase change. So when you look up here and you look at these elements here, so here's an element, you see that there is a disorder number. Your delta H can be zero, and so can your delta G, but not your S when you're looking it up in a table. So this is a quantitative problem, and so I'm going to look at my delta S and calculate that by taking products minus reactants. So put your numbers in. I like to use brackets to keep the products and the reactants separate. Remember, the elements are not zero when you're calculating delta S. And my final answer, I get a negative 11 joules per Kelvin per mole. So this is a decrease in disorder. And we see that our number is really small. And so that's very typical for these delta S's to have a very, very small number.